To lecture 17. In this lecture, we will discuss the four functions theorem, which is a significant generalization to the Kleitman's inequalities that we have been studying in the last two classes. This is not the first generalization to Kleitman's inequalities. In fact, we had mentioned there are other generalizations also. And this FGG is a very useful and famous generalization. But the plan is to jump right to the most general version, which is the four functions theorem. And then maybe in the later classes, we will, using the four functions theorem, we might try to derive the intermediate generalization. Okay, so our first agenda today is to understand the four functions theorem. Secondly, we will use four functions theorem. Before proving the four functions theorem, just to get a familiarity, we will use it to prove the Kleitman's first result, the uniform distribution result. And then the main agenda for this lecture is the last one, which is to prove the four functions theorem. Okay, so in order to state the four functions theorem, we need some notations. It's not difficult. I mean, these are all natural notations, but there are some 3-4 notations to familiarize ourselves with. Okay, so we are talking about some functions from a power set of numbers 1 to n. Okay, so the each element in the domain is a subset of n, and the codomain is non-negative real numbers. Okay, so even though I will denote it by r plus, it does not mean strictly positive, it only means non-negative. Okay, and the same function definition phi, we will overload it. Okay, the default argument to phi is a single subset of 2 power n, but we will use the same notation also to denote a collection. You know, you'll apply this function also to a collection of subsets of n. Okay, in which case the definition of the phi of the collection will be just sum over phi values at all the sets in the collection. Okay, very natural extension to the definition. You can already think that this is the case if they were, sample space, then each subset is an element of the sample space. If you can think about phi of A as a probability, it needn't be, because see, it's just r plus. Phi values can be more than 1. But I mean, just to get the intuition clear, if phi was like a probability assigned to each subset in the family, then this is the natural definition for the probability of a collection of sets, just sum of the probabilities. But here it's just sum of the function values. Okay, and we also define this to different kind of union and intersection operations, where, remember, in the Kleitman's and in the last class, when you take union of two families, it just meant the union of two families. But this double union is, by the way, the Allen and Spencer book uses the same union symbol for both this definition as well as the classical definition of union, just that the size of that symbol is a bit different. But in order to clearly distinguish the two cases, I am introducing a new symbol, which I'll call it as the the double union, and this as the double intersection. Okay, so the double union of two families is, you go inside each family, pick one set from the first family A, from this first family script A, and B from the second family script B, and then take their union. Okay, so yeah, this is what, so for example, if this script A has m, this collection has m sets and this collection has n sets, you may have at most m times n many sets here, whereas in a normal union it could only be at most m plus n. Okay, because each pairwise you take a union, but some of them may collide. Maybe some A1 union B1 will turn out to be another A1 union A2 union B2, and hence it's not necessary that you will have mn elements, but it can be as high as mn. Similarly, the double intersection is also defined as you go inside of the families and then take pairwise intersections. Okay, so this is more correctly referred to as the collection of pairwise intersections. Collection of pairwise intersection. Similarly, the double union is the collection of pairwise union. Okay, yeah, and note that in general, this we already mentioned, this double intersection can be very different from an ordinary intersection. But there is one interesting case where the double intersection kind of boils down to being equal to the ordinary intersection of families. Okay, and that is when A and B are downsets. Okay, so I claim that if both A and B are down sets, I am not going to repeat its definition, then A double intersection B, the family, the double intersection of the families or the collection of pairwise intersection is nothing but the intersection of the two families, the classical intersection of the two families. This only collects those sets which are in both the families, both in A and in B. Okay, the proof is straightforward. I'll just run through it, but I'll recommend that you actually pause here and then pick any subset in this A double intersection B, show that it is in A intersection B, and conversely pick any set from A intersection B and show that it is in A double intersection B. Okay, at least this side should be very easy, right? If a set is in A intersection script A intersection script B, that means it's in both the families. So when I am doing this pairwise intersection, I am allowed to take S intersection S. If S is in both in A and in B, then I am allowed to take S intersection S, which is equal to S, which tells you that S is in this family also. In fact, yeah, that's the easy direction, and that's what I have written first. If you pick anybody from here, then it qualifies to be both the A and the B in this intersection, and hence it is there. Okay, and now, by the way, here we did not use the property that these families are down sets. So this is true in general. Okay, A intersection B is a subset of A double intersection B. That's true for any two families A and B. The other side is where we will use the fact that they are down sets. Okay, now suppose S is a member of this A double intersection B. What does that mean? That means S can be written as some A intersection B, where A is from this first family and B is from the second family. This is the definition of pairwise intersection, right? So now if S is this tells you that if S is A intersection B, that means S is a subset of A, right? It is A intersection something, it can only be a subset of A. Similarly, it is also B intersection something, so S can only be a subset of B. But both script A as well as script B are down sets, remember, okay? Since they are down sets, any subset of A is also a member of A, because A is in script A and S is a subset of A, hence S is also in script A. Similarly, your B is in script B, S is a subset of B, and hence the subset is also in script B. Okay, so which means S is in both the families, and hence in their intersection. Okay, so this proves this claim that if the A families A and B are down sets, then the pairwise intersection family is equal to intersection of the two families. Now, as an exercise, you can show that the same thing is true even if you assume A and B are upsets. No, not the same thing, sorry. So here maybe I should highlight that, this is an exercise for you. Show that their pairwise union also turns out to be the intersection, the classical intersection. Okay, that's a bit funny, but I want you to work it out by yourself, okay, rather than me giving. Okay, so this is the amount of notation we need to study or to state the four functions theorem. One is this overloading of a function operator, where you define it on subsets, but then extend the definition to collection of subsets via the usual addition. And secondly, this notion of pairwise intersection family and pairwise union family. And also we need to keep in mind this observation that the pairwise intersection and the classical intersection are the same for downsets. Okay, with this, let's state the four functions theorem, which I'll abbreviate as 4FT due to Ahlswede and Daykin. Okay, so as the name suggests, we have to talk about four functions. Okay, so these four functions we will denote as alpha, beta, gamma, delta. Each of them is from 2 to the power n, the power set of n, to non-negative real numbers. Okay, remember this plus does not mean strictly positive, it means non-negative real numbers. Okay, so all these functions are from not n but the power set of n to r plus, right? So you have one function alpha, you have another function beta, and so on. Okay, there are four such functions from this to this. Okay, now the four functions theorem states that if for any two members of the domain, so this AB subset of n is equivalent to saying AB members of the domain, right, 2 power. if for any two members of the domain, if alpha times A, if alpha of A times beta of B is upper bounded by gamma of A union B times delta of A intersection B. Okay. Now, this may look a bit crazy in the beginning, but yeah, there is no other go, but you have to, but we'll use it so many times that after a while you would kind of, mechanically fill in the equation, right? So, okay, if this is satisfied, then this is also satisfied. But what is the conclusion? Conclusion you should interpret a bit more carefully. The hypothesis is on single elements or single members of the family. I agree that the members themselves are sets, but again, right, these are about single a set A and a set B, whereas the hypothesis is about a family of sets script A and a family of sets script B. Okay, so remember this was a subset, A and B were subset of n. This is subset of 2 power n. Okay, and we claim that the same expression holds, but with script A taking the role of capital A, script B taking the role of, this is a script B. Okay, script B taking the role of capital B, and the pairwise union of families taking the role of this set union, and pairwise intersection of the families taking the role of the set intersection. Okay, so alpha of script A times beta of script B is upper bounded by gamma of the pairwise unions of the families and delta of the pairwise intersection. Okay, this is the theorem. Okay, so remember the alpha here is one function and the alpha in the conclusion is the overloaded version of the function. Same thing applies for beta, gamma and delta. Okay, so now before proving this theorem, our agenda is to show that this 4 functions theorem, it implies the non-uniform Kleitman also, but that I'm planning to leave it as an exercise. The part I'll do in the lecture is to show that the uniform Kleitman follows from the 4 functions theorem. Okay, so how do I do that? So now this 4 functions theorem, I can pick any 4 functions subject to some constraints. So I am going to pick alpha, beta, gamma and delta to be characteristic functions of these 4 families, the script A, script B, the pairwise union and their pairwise intersection. So you know what is a characteristic function of a set? It assigns 1 to all members in the set and 0 to every member outside the set. But remember here the member itself is a set. Okay, so for example, what is alpha of S? Alpha of S will be 1 if S is a set in the family, and it will be 0 otherwise. Okay, so yeah, I have just expanded alpha, but you can write similar expressions for beta, gamma as well as delta. Okay, so now what is given to you, we have to verify whether the hypothesis or the premise of 4 functions theorem is true. Okay, that is, this product, is it true for every subsets? Okay, so take any 2 subsets A and B. All right, so yeah, take any 2 subsets A, B and N. Is it true that alpha A times beta B is less than or equal to gamma A union B times delta A intersection B? Yeah, it turns out to be true, but you have to do a very small case analysis. Okay, so if either A is not in the family script A, in which case alpha A will be 0 because alpha is the characteristic function of the family script A. So if A is not in that, this is 0. If B is not in script B, then beta B is 0, which means the left hand side is 0. And now the right hand side, gamma, delta are all non-negative functions, so the right hand side is 0 or more. Hence, this inequality is satisfied if at least one of them is not in the corresponding family. But if both of them are in the family, that is A is in script A and B is in script B, then what about A union B and A intersection B? So if both of them are in the family, then the left hand side is 1. 1 times 1, 1. Which means the right hand side also has to be 1 because it's a characteristic function. The product can only be 0 or 1. Okay, though the theorem applies to any positive or non-negative real valued functions, since we are picking characteristic functions, that's the only possibility. But that's easily ensured, right? Because by definition of this double union, the pairwise union, if A is from this script A and B is from script B, then A union B is a member of the script A double union B. Okay, so this will be 1. Similarly, since A is from the first family and B is from the second family, by definition of the double intersection, this A intersection B is a member of the double intersection, and hence the characteristic function delta of it evaluates to 1. Okay, so this inequality becomes 1 less than or equal to 1, which is also satisfied. Okay, so yeah, so which means these 4 functions satisfies the definition of or the requirements, the premises for the 4 functions theorem. Hence we can say that the conclusion is also true. Now what is the conclusion of the 4 functions theorem? Alpha of the family, first family, times beta of the second family is upper bounded by this. Okay, now let us try to now convert that in terms of, remember what is the Kleitman's inequality? This is A times B less than or equal to size of A intersection B times 2 power, right? This is what we have to prove. But alpha of A is easily, it's a characteristic function, but now since it's of the whole family, you essentially sum the characteristic function of this whole thing, which will be 1 plus 1 plus 1 as many times as the number of sets in this family, cardinality of the family. Similarly, beta B, remember this is the overloaded beta, so it's adding up all the beta values inside of B, script B, which means adding up 1 cardinality beta B, script B times. Okay, so this is left hand side is okay. Now for the right hand side, remember that this A double intersection B, this is the first time that we are using the fact that it's a down sets, okay, that A and B are down sets. Since A and B are down sets, we already showed that A double intersection is B is same as the classical intersection. Okay, so this is delta of A intersection B, and hence it is nothing but the number of elements. Once you number of elements in this family, script A intersection script B, because delta is just the characteristic function of that family. Now that leaves us with gamma A double union B, but remember the script A double union script B is still a power set of 2 power n, hence it cannot contain more than 2 power n. It's a power set of, it's still a subfamily of the power set, so it cannot contain more than 2 power n elements, and this is exactly the Kleitman's uniform Kleitman's expression which we wanted to prove. Okay, so as an exercise, this is a slightly difficult exercise. You can prove that the non-uniform Kleitman also using just the 4 functions theorem. Okay, so if you think about the cardinality, ideally, if you are stuck on how to proceed with this exercise, you can first try to define this to be, rather than alpha s being the characteristic function, you define it to be 1 by 2 to the power n. Okay, so instead of that would be the probability that a randomly chosen uniformly at random chosen subset of n is equal to this set S. Okay, so that will be 1 by 2 to the power n, and then you proceed with the computation, and then you will see that the same thing will hold. And now if you replace that 1 by 2 power n with the probability of actually picking S in a non-uniform setting, you will be able to prove the non-uniform Kleitman. Okay, but I leave it as an exercise. I'll put it in the tutorial also. Okay, so that's 20 minutes. Maybe we will take another 40 minutes to prove the 4 function theorem. Okay, so yeah, in so much of symbols, this is what it means. For any 4 functions from the power set of n to r plus, if pairwise each set satisfies this expression, if every A and B subset of n satisfies this, then every family script A and script B, not necessarily down families or anything, every 2 families script A and script B satisfies the same expression with the overloaded version of the functions, and union replaced by the pairwise union of families, and intersection replaced by the pairwise intersection of the families. Yeah, so this is because there are so many notations and so many things, the proof will be much clearer if we do some pre-processing, some massaging to the conditions. Okay, so we will do certain things which will not really change what we are trying to prove. So yeah, the following changes will not affect. We'll show why it won't affect any conditions above. Okay, so firstly, remember this alpha you have to define for every subset of n, but this alpha is getting applied whether it is in the premise or in the hypothesis only to members which are in script A, right? So yeah, technically speaking, the premise applies to every A, but we only are in the conclusion at least, we are only using for those A which are in script A. So by varying the value of alpha outside of the family script A, I may be changing something in the premise, but nothing changes in the conclusion. Okay, so yeah, so what I'll do is I'll set this alpha to be 0 for every set outside of the script A. So every set outside of the script A, okay, remember that. And similarly, I'll set beta to be 0 outside of script B, right, all of that. And gamma to be 0 outside of this A pairwise union beta, which is, you look at the conclusion line, and that will tell you where you should tweak each function. Similarly, delta is set to 0 outside of its argument family, which is the A double intersection B. Okay. Anyway, the hypothesis, the conclusion you see does not get affected at all. And in the premise also, whatever where it will only be, at least it will be true for the cases where A as well as B is in your set. Okay. So, and maybe we should also argue that, like suppose you had originally, you satisfy this premise with these conditions, you will have to argue that you will actually be satisfying it with the new conditions also. All right. If it's a change in the left hand side, I am not worried, because you are only going to this was a 0. So that is, I can make the premise weaker, but I am not allowed to make the premise stronger. So by setting it to 0, I don't say anything. But setting this to 0 is asking for a bit of trouble. But then again, it matters only when both A and B are in the family, as long as, because otherwise here itself, left hand side itself will be 0. So the left hand side remaining unaffected and right hand side vanishing to 0 can potentially happen only when A is from the first family and B is from the second family, in which case A union B is also in this pairwise union family, hence you will not tweak it, and A intersection B is in this family, so you won't tweak it. Okay. So so the only case where the premise gets tweaked is by the left hand side becoming 0, and then it is okay whatever you do to the right hand side as long as it is 0 or more. Okay, so this is safe to do. But now this is not all, but more than this, after you do this, now forget the old functions alpha, beta and gamma and delta. These are the new functions. Okay, I don't want to introduce a prime here because we are going to stay with this alpha, beta, gamma for long. I don't want to clutter the notation. So from now onwards, when I say alpha, beta, gamma, delta, I mean the functions after this modification is done. But now after this modification is done, I really do not have to worry about alpha of script A. I can actually take alpha of the entire power set. Right? Even if I take alpha of the entire power set, it is still going to be equal to alpha of A. Why? Because I have set for all the sets outside of the script A, I have set its alpha value to be 0. So when you are adding things up, these zeros won't contribute. So alpha of A is equal to alpha of the power set. Similarly, beta of this family is equal to beta of the power set. This is gamma of the power set, and this is delta of the power set. Okay. So the conclusion, after you redefine this, I can redefine the conclusion with script A to be the whole power set and script B also to be the whole power set. Okay. So this is the pre-processing that we do. We have redefined alpha, beta, gamma, delta so that they take on value 0 outside of the given families, and hence in the conclusion we can replace those families with the entire power set. Okay. So now we are ready to do the proof. The proof is going to be via induction on N, the size of the ground set. Okay. So here I am doing it a bit differently from the textbook from Allen and Spencer. There n equal to 1 is taken as the base case. I'm sure it's not because they, and that's difficult, and that's a difficult base case, okay. N equal to 0 is far easier compared to n equal to 1. But Allen and Spencer does that because doing the n equal to 1 base case actually helps you in proving the induction step also. Okay, but what I am going to do is, in order to keep the logical complexity minimum, I will only prove the base case for n equal to 0 and directly prove the induction step. But this induction step is going to be more complicated than how the induction step is proved in the textbook. But the n equal to 1 base case, I don't have to deal separately. Okay, so for when n is equal to 0, what is the power set of so this means your n is nothing but the empty set. So your 2 to the power empty set is nothing but a family which contains only the empty set. Okay. Now, what was the hypothesis for any two members A, B, and A and B, subset of what? Subset of the empty set, right? So for any two subsets A and B, subsets of the empty sets, which means they can only be phi because that's the only subset available. So this hypothesis only essentially reads when n is equal to 0, it only applies to both A and B being phi. Okay, and then this A is phi, B is phi, A union B is phi union phi, which is phi, A intersection B is phi union phi, which is phi. Okay, so what is given amounts to this: A times A of empty set times beta of alpha of empty set times beta of empty set is upper bounded by gamma of empty set times delta of empty set. Okay. Now, what is the required conclusion? The required conclusion, remember, now is on the entire power set. Okay, alpha of the entire power set times beta of the entire power set, etc., etc. But the entire power set here, what is 2 power n is just the set phi. Okay, so alpha, or for that matter alpha, beta, gamma, or delta, but I'll just write it for alpha. Alpha of 2 power n in this case is nothing but alpha of 2 power phi, which is alpha of this singleton family, which by definition of the overloading of alpha is just sum over every set in the family alpha evaluated at that set. But since now there is only one term to sum, I don't need to write the sigma. So this is nothing but alpha of phi. Okay, so this is alpha of phi. By similar argument, this is beta of phi, this is gamma of phi, this is delta of phi. So in some sense, the n equal to 0, the hypothesis that is given to you is exactly the conclusion that you require. So there is nothing to prove. It's only about making sure that you interpret A and 2 power n clearly. Okay. Okay, so with that, we are ready to, with the base case for n equal to 0 done, we are ready to move to the induction step. Okay, so in the induction step, we will assume that your n is at least 1. Okay, yeah, so what is the induction hypothesis for every 4 functions? Okay, remember, not just, this is for every 4 functions from n, oh, this is wrong, I should have written 2 to the power 2 to the power n minus 1 to non-negative real numbers. Suppose they satisfy this condition for every A and B subset of, again, note n minus 1. If this condition is satisfied, then alpha of the power set of n minus 1 times beta of the same thing is less than or equal to gamma of the same thing times delta of the same thing. This is the induction hypothesis. The aim is to show that these alpha, beta, gamma, delta are not same as the previous. This is for every alpha, beta, gamma, delta. Again, I don't want to introduce just primed notations for a minor thing, right? This is just a for all. This in fact, these are not free variables because it's a for every. These are just variables that are part of the for all quantifier. Okay, yeah, but this is given to you. This alpha in the target, this alpha, beta, gamma, delta are some given 4 functions from, again, this is a mistake, 2 to the power n to r plus, where they satisfy this condition for every pair of subsets A and B from subsets of n. Okay, so this condition is satisfied. This is given to us, and we should prove using this premise, as well as we can resort to using the induction hypothesis. We have to show that alpha of this power set of n times beta of the same is upper bounded by gamma of the same times delta of the same. Now we are going to define 4 new functions based on alpha, beta, gamma, delta. Now at least, since we are going to use them together, I am going to use the primed notations for them: alpha prime, beta prime, gamma prime and delta prime. But these functions, remember, are from 2 to the power n minus 1. Okay, remember, alpha, beta and gamma are from 2 to the power n, but alpha prime, beta prime, gamma prime, delta prime are from 2 to the power n minus 1. Okay, and what is the definition? Now this phi is a placeholder for either alpha, beta, gamma or delta. Okay, and phi prime correspondingly would mean the primed version. Okay, so for any subset of numbers 1 to n minus 1, I have to define what would be phi prime of s. I am given the definition of phi of s, I have to define phi prime of s. So phi prime of s is defined as phi of s plus phi of s union n. Okay, now remember, here there is no, remember on the right hand side there is no phi prime. Okay, so this is phi prime, and I am careful that s is from a subset of n minus 1, but here since it is phi, I can actually use s union n. This also contains n, but that is fine because phi is defined on 2 power n. Okay, so this is the definition of phi prime. You just add up its with the phi value on that set plus phi value of that set together with n. Now this, as I said, this phi is just a placeholder. Instead of writing 4 different definitions, I just wrote one definition by using. So you can write 4 things like alpha prime s is alpha s plus alpha s union s, beta prime s is beta s plus beta s union n, gamma prime s is gamma s, and so on, gamma plus gamma of s plus gamma of s union n, and so on. Okay, but with this, now if I compute what is phi prime of 2 to the power n minus 1, the subset of power set of n minus 1, it turns out that you will actually add up the phi values, not the phi prime values. If you add up the phi prime values of all the guys here, you will actually add up phi values of double the number of guys. Okay, because every phi prime value here is already a sum of 2 guys, so, and exactly the guys you want. So this you can easily verify that, right? This is a critical thing. Right, this tells you that now, remember, what we have to prove is alpha of this entire power set, beta, etc. satisfies this. But now, because of this thing in the box, I can replace this alpha 2 power n by alpha prime 2 to the power n minus 1 power set, beta prime 2 to the power n minus 1, and so on, right? Each of these 4 2 to the power n, I can replace it with 2 to the power n minus 1, the power set of n minus 1, and each alpha, beta, gamma, delta, I'll replace with alpha prime, beta prime, gamma prime. Okay, and hence this conclusion I would get provided I prove I have a similar conclusion for alpha primes or the primed functions with 2 to the power n minus 1. But do I have such a thing? Okay, it looks like it just follows from the induction hypothesis, because alpha prime, beta prime, gamma prime, delta prime are functions in the appropriate space, and we have already assumed the induction hypothesis. But what is missing is that the induction hypothesis, or this, because the entire 4 functions theorem is a conditional statement, the induction hypothesis is also a conditional statement. So this will be true only if this premise is true. Okay, which means we have to really now go and verify this entire premise. Okay, this is what we have to now verify. If this premise is true, then because of induction hypothesis, this conclusion is true, not for which 4 functions? For alpha prime, beta prime, gamma prime and delta prime, and that is precisely what we want here. Okay, so yeah, the rest of the proof is about proving the line in yellow. For which functions? For alpha prime, beta prime, gamma prime and delta prime. Yeah, so that's what I have written here. So what we want would follow from the induction hypothesis, provided these 4 primed functions satisfy the premise of the induction hypothesis, which, if you write it out in full, means for every pair of subsets A, B of n minus 1, this is true. Okay, so this I'll denote by star star. Okay, now what is the left hand side of this inequality? This is alpha prime A, beta prime B, which by the definition, using the definition of alpha prime and beta prime, I can expand it as follows, right? Alpha prime of A is alpha of A plus alpha of A union N. Similarly, beta prime of B is beta of B plus beta of B union N. Similarly, the right hand side, the gamma prime of A union B is gamma of that set A union B plus gamma of that set union N, which is A union B union N. Similarly, delta prime is delta of that set plus delta of that set union N. So remember, this is an A intersection B union N. Okay. Remember, one is an intersection, one is a union. Okay. So now let me, these 8 guys, let me give them some symbols. Right? This alpha of A I'll denote as alpha 0, alpha of A union N I'll denote as alpha 1. Similarly, beta 0, beta 1, gamma 0 is gamma of A union beta, A union B, gamma 1, gamma delta 0 and delta 1. Okay. So what I have to prove is finally this claim, right? Alpha plus alpha 1 times alpha naught plus alpha 1 times beta naught plus beta 1 is at most less than or equal to RHS. This is RHS. Less than or equal to RHS, which is gamma naught plus gamma 1 less than or equal to delta naught plus delta 1. But that's what we want to prove. But let us also see what are the given conditions, this term by term products, what can we say? Okay, so we know that alpha, beta, gamma and delta satisfies the conditions for the 4 functions theorem, which means if you consider alpha A times beta B, which is alpha naught, which is this alpha naught intersection beta naught, it is at most gamma of A union B times delta of A intersection B. So gamma of A union B times delta of A intersection B, which is gamma naught, delta naught by the names we have assigned to them. By the way, this is already satisfied. Why? Because this is in the premise of what we are trying to prove, and hence we can assume that, right? I'm using this. So this is already given to us. So alpha naught, beta naught is at most gamma naught, delta naught. Similarly, what about alpha of A times beta of B union N? Now B union N is another set. Okay, let me call it B prime. Right? Now, this should be because alpha, beta, gamma, delta satisfy the premise, this should be gamma of A union B prime, which is gamma of A union B union N. Okay, this one, gamma 1, and delta of A intersection B prime. But now A does not contain N, so A intersection B prime is just A intersection B. Right? So you get gamma 1, delta 0. So remember, there is a change of sign here, alpha naught beta 1, but it is gamma, gamma 1 delta 0. Okay. Now similarly, you can verify for alpha 1 beta 0, which also is the same, and alpha 1 beta 1. Okay. Alpha 1 beta 1 would contain N in both the cases. So both the intersection as well as the union, you will have to pick from those which contain N, and hence it will be gamma 1 delta 1. Whereas if only one of them contain N, then the delta will always be the 0 delta because N will not be there in the intersection. Gamma will always be the gamma 1 because union will contain this. Okay. So stare at these relations, these 4 inequalities for some time. It's very easy to make a careless mistake here because you may be tempted to write alpha I beta j less than or equal to gamma I gamma j. This is wrong. Okay, this is wrong for this case at least. Other cases kind of follow it, but this case it is wrong. So these are the given conditions, hence we can assume that. I call it the dagger. Okay, and what is our whole aim? Our aim is to show that if dagger is true, then this alpha naught plus alpha 1 times beta naught plus beta 1 is upper bounded by gamma naught plus gamma 1 times delta naught delta. Okay. So if we can show this, then we are done. We can prove the double star and done. Okay. So the induction step, this is what we have to do to prove the induction step. So the induction step at its core is actually just a property about, or a property about 8, not 4, property about 8 non-negative real numbers. If you see this, this involves 8 real numbers, alpha 0, alpha 1, beta 0, beta 1, etc. Gamma 0, gamma 1, etc. Right? So this is a fact about just 8 real numbers. We can forget everything. Right? Now we only have to prove this claim about 8 real numbers, and the proof of the 4 functions theorem is complete. Okay, so this claim I will kind of, this is my name, not a standard name. I'll call it the 8 numbers theorem. Okay, so in order to prove the induction step, the key step in the proof of the 4 functions theorem, it's enough to prove this claim, which we will call the 8 numbers theorem. So this says that for every 8 non-negative numbers, alpha 0 all the way to delta 1, again R plus, remember, is true for non-negative numbers. If they satisfy these 4 inequalities, which we have read out many times, then this expression is true. Okay, so here all I want you to appreciate is that we have reduced it to something about 8 numbers. We can forget about functions, the domain, the power set, whatever. Okay, it's just and hence, since it's about 8 numbers, we will actually give a picture proof for this fact. Okay, it's a proof by pictures for this 8 numbers theorem. Okay, so this is how I am going to represent these 8 numbers as 2 rectangles. The first rectangle has alpha 0 plus alpha 1 base, beta 0 plus beta 1 as its height. The next guy has gamma 0 plus gamma 1 and delta 0 plus delta 1 as its height. Okay. Now I have marked each of this rectangle as R1. So remember, L1. L1, what is the area of L1? It is alpha 0, beta 0. What is the area of R1? It is gamma 0, delta 0. So the first guy here, alpha 0, beta 0, less than or equal to gamma 0, delta 0. Yeah, I actually written it here. This is star 1. Remember, this is star 1, star 2, star 3, star 4. And this I call, the conclusion I call as a star 8, which is what we want to prove. I call it as star 8. So star 1 essentially says the area of L1. So when I say capital L1, I mean the area of L1. Okay. So the L1 is less than or equal to R1. Now, what is star 2? Remember, star 2 is where the subscripts are in the non-intuitive order. So it says alpha 0, beta 1. Alpha 0, beta 1, which means L2 is less than or equal to gamma 1, delta 0. Right? Gamma 1, delta 0, which means R3. So yeah, this is where there is a change. L2 is not upper bounded by R2. It is upper bounded by R3. Similarly, the third expression essentially means L3 is upper bounded by R3. Fourth one means L4 is upper bounded by R4 in area. Okay. So yeah, this I think it's best if you can actually maybe I can zoom it for you so that you can verify that these are what these 4 inequalities mean in terms of this picture. If instead of this R3, if we had R2, there was nothing to prove. By the way, what do we have to prove? The required conclusion is this, right? Alpha 0 plus alpha 1 times beta 0 plus beta 1, which is nothing but the full area of this rectangle, these 4 pieces added together. Okay, that is the left hand side of the inequality we want to prove, and the right hand side is the full area of the second rectangle. Okay, gamma 0 plus gamma 1, right? So that's what we want to prove. So if this R3, if instead of this R3 we had R2, there was nothing to prove. Okay, we are just saying that 4 numbers which are component wise less than 4 other numbers add up in the when you add them up, the smaller guys add up to a smaller value than the larger guys. So that's all. So but this is what makes the whole thing non-trivial. Okay. Now at this point, I strongly encourage you to kind of pause and check for yourself whether you can prove it by yourself, the picture proof by tweaking this and so on. If you can do it, excellent. If you cannot do it, when I'm going to, you can continue seeing the lecture, but at some point, maybe you want to actually pause and go the rest of the route by yourself. Okay. So we do now another pre-processing. Remember, we already had done a pre-processing long ago, but this is a different one. Okay, so in this, our attempt is to reduce these 8 numbers to 4 numbers. In fact, people say that human beings cannot hold more than 5 or 6 numbers in the mind at the same time. That is why you tend to remember 4 numbers not digit by digit, but 2-digit or 3-digit numbers, you split them into and try to remember them. Okay, yeah, but anyway, I'm not an expert on psychology, so that's not that. Anyway, in order to keep our proof simple, we are going to reduce these 8 numbers to a set of 4 numbers, and to do that we actually shrink this rectangle, once from the left, okay, this edge we will kind of, move inward. We know that L1 is less than or equal to R1. So R1 is the larger, R1 is bigger than L1 in total area, in its area. So I'll shrink R1 by moving this left boundary, left margin inward till L1 is equal to R1, okay. Now this does not affect any other inequality, right? Why? Because L2 also only, okay, by the way, nothing else changed, only the R2 and R1 changed, but R2 does not picture in any inequality. So, right, R2 does not picture in any of these four guys, so this hasn't affected the premises, okay. This has actually reduced the total area of this rectangle, but if we can prove the claim with the smaller rectangle, it is true for the original rectangle, right? Because we are proving that this is a larger than this, okay. We are proving that this is larger than this, so reducing this and proving it is even better, okay. So this is the first thing that we do, and then we actually bring down the top, okay. Remember, L4 is less than or equal to R4, so R4 is the larger one. Bring it till the point that the area of R4 agrees with that of L4, okay. So this gives you two equalities where you originally had inequalities, and again, nothing changed. The only other rectangle that changed its area was R2, but that's not part of the premises, and the total area only went down. Hence, if you can prove that this is larger still than the left, you are done, okay. So yeah, that's what we have done first. We can assume without loss of generality by shrinking, okay. This two shrinkings that we said, that R1 is equal to L1 and R4 is equal to L4. So in terms of the 8 numbers, it is R1 is alpha naught beta naught, this is gamma naught delta naught, this is alpha 1 beta 1, this is gamma 1 delta 1. Now, yeah, and as I said, nothing has changed for L2, L3 or R3. So those inequalities still hold. Both L2 and L3, that is the equations 2 and 3 are still less than or equal to R3. Remember, during this process, R3 was protected. We only moved this left margin and the top margin. Nothing has touched R3. Okay. So now this L1, L3 less than or equal to R3, I expanded back in terms of the 8 numbers. So L1 is alpha naught beta 1, L3 is alpha 1 beta 1. You can verify all of this. Okay, pause and verify. But now what I'll do is I'll divide both. By the way, these are two inequalities. I could have actually written them as separate thing. L1 less than R3 and L3 less than or equal to R3. And then I divide the left hand side with alpha naught beta naught. I divide the left hand side with alpha naught beta naught and the right hand side with gamma naught delta naught. Okay. So you see some things cancel out. Alpha naught cancels out. This leaves beta 1 by beta naught. Here the beta naught cancels out, leaving alpha 1 by alpha naught. Here the delta naught cancels out, leaving the gamma 1 by gamma naught. So this beta 1 by beta naught I'll call as B. This alpha 1 by alpha naught I'll call as A. Gamma 1 by gamma naught I'll call as C. So I have 3 of the 4 numbers I am looking for, and these are their definitions. Okay. Now one is pending. Where does it come from? We still know that L4, in fact we know L1 equal to R1, but if you substitute, you will and then divide by these things, you will only prove 1 equal to 1. You don't get anything from there. But with L4 equal to R4, which means this guy here, alpha 1 beta 1 equal to gamma 1 delta 1. If you divide it by alpha naught beta naught on the left hand side and gamma naught delta naught on the right hand side, you see nothing cancels out, but this alpha 1 by alpha naught is already a number we know, which is A. Beta 1 by beta naught is already something which we said to be B. Gamma 1 by gamma naught is something which said to be C. And that tells you what should be your fourth number. That is delta 1 by delta naught, which is D. Okay. So now this condition, this 4 inequalities, which the premise which was in terms of some 8 numbers, the premise at least we have reduced it to something about 3 numbers, which is A less than or equal to C, right? See, that's what, this L1 less than or equal to R3 finally reduced to B less than or equal to C. L3 less than or equal to R3 finally just reduced to A less than or equal to C. That are the first 2 conditions. And this L4 equal to R4 reduced to AB equal to CD. But what is the thing that we wanted to prove? We wanted to prove this inequality, right? But here also I can pull out alpha naught from the first brackets and beta naught from the second bracket. So alpha naught beta naught comes out. What is inside of this bracket? 1 plus alpha 1 by alpha naught, which is 1 plus A. Here you have 1 plus beta 1 by beta naught, which is 1 plus b. Similarly, here I pull out gamma naught from the first bracket and delta naught from the second bracket to get gamma naught delta naught 1 plus c 1 plus d. Now remember, these two are the same, right? Alpha naught beta naught is equal to L1, which is equal to, then gamma naught delta naught is equal to R1. But remember, those are these L1 and R1 whose area we had kind of made equal by this pulling the left margin in. So they cancel out, and only 4 numbers are left in what we want to show also. Okay, so it is enough to show that 1 plus a times 1 plus b is at most 1 plus c times 1 plus d. Just expand it and you see that 1 and 1 will cancel out. And this a, b and c, d, remember we already know from this condition that a, b and c, d are the same. So that will also cancel out. So in some sense, now the whole 8 number claim has boiled down to showing this claim for 4 numbers. If you can assume that c is more than a and b, okay, we are given that c is a number which is more than the max of a and b, more than both a and b, as well as ab equal to cd, can we show that a plus b is less than or equal to c plus d? Okay, so this is a 4 number theorem if you wish, but this has a very cute picture proof if I haven't made a mistake. By the way, in the Alone and Spencer book, this is given more algebraically, so I recommend that you go back there and also verify it, and also think very carefully about this proof and make sure that there is no mistake in the way I have tried to. I think I have, it took me around 2 days to convert this into a picture proof, okay, and I might have made some mistakes because there is always a time pressure to record without too much of a, without pushing it very close to the tutorial day. Okay, so yeah, so this is what we want to prove. Now this, I am again drawing 2 rectangles. One is an a by b rectangle, the other is the back one, and the brown one is a c by d rectangle. We know that both these rectangles have the same area because of the third condition, AB is equal to CD, and we know that this rectangle, the brown rectangle, is even more elongated than the AB rectangle because one side of the CD rectangle is larger or equal to the largest side in the AB. Okay, I mean again this can be an equal also, but yeah, it is either equal to or more elongated than the black rectangle, right? And now you know that when 2 rectangles have the same area, more elongated ones have the larger perimeter. And now you see that the conclusion that we are looking for is essentially a relation among the perimeters, right? In fact, twice of a plus b would be the perimeter of the black rectangle, and the twice of c plus d would be the perimeter of the brown rectangle. Okay, so since CD is a more skewed rectangle than AB, its perimeter has to be larger, and that is what this 4 numbers theorem would say. And the 4 numbers theorem would imply the 8 numbers theorem, and the 8 numbers theorem would imply our 4 functions theorem. Okay, so this finishes the proof of the 4 functions theorem. And yeah, let me just scroll down to the statement and then stop it there. Okay, yeah, thank you.